Integration by parts day 2. We're just going to do a bunch of examples here. I think it's kind of strange we're spending 2 days on something you don't need to know how to do in AB, but it should make you a lot better at U substitution. Hopefully, you're already starting to evaluate indefinite integrals that contain products using integration by parts. And hopefully you're starting to see that those products are the results of product rule, not chain rule. That's the main thing we have to decide. Except sometimes, like you saw with the antiderivative of natural log, you use integration by parts when you really don't have any other options. So we're going to use this formula. The integral of u dv is uv minus the integral of v du, but we're not really going to do it that way. We have almost a geometric structure, a visual, to help us remember. So let's start off with the first example. In this example, we're actually going to do twice. You're going to see there are multiple correct ways to do things sometimes. And so some students think, well, shoot. Try that again. Some students think that u should be natural log of x, and you're going to see that works. And if that's the case, everything else, the other natural log of x, goes along with the dx to make dv. So that makes du 1 over x dx, and that makes v the antiderivative of natural log of x, which we did in the last video, x natural log of x minus x. So we draw in our little 7, and the first thing we write is natural log of x times x natural log of x minus x, uv. So these two across the top, and maybe I'll draw in that little 7, right? We're multiplying the top two across the top, and then minus the integral of x natural log of x times 1 over x. And I decided not to simplify that yet. I think that's a little bit better. But we can divide out an x and divide out another x. And over here, let's say x natural log squared minus x natural log of x. And now we have a much cleaner minus the integral of natural log of x minus 1. And again, the antiderivative of natural log of x is x natural log of x minus x. And then the antiderivative of 1 is x. Don't forget to recopy these first two pieces. We're going to go ahead and simplify one more time because x natural log squared x is fine, but we have two of these minus x natural log of x's. So minus 2x natural log of x, and we have minus 2x's and our constant. But there's another way to do this one. So if you say u is equal to natural log all squared, it actually works out. So in this case, let's see, u is natural log of x squared. Chain rule would be 2 times natural log times the derivative of natural log of x, 1 over x. And if dv is dx, then v is equal to x. So again, across the top, our first thing, and I lost it. Our first thing is going to be x natural log squared x. I have a feeling it's going to animate later. Minus the integral of x times this 2 natural log of x over x. So we just get the integral of 2 natural log of x dx. And antiderivative of natural log is x natural log of x minus x. We have to distribute that 2, and we get x natural log squared x minus 2x natural log of x. And then distribute that 2 again, plus 2x, haha, got it, plus a constant. All right, so how are we going to evaluate cosine of natural log of x dx? Well, that one's actually a little bit weird, you're going to see. We're going to choose u to be the entire cosine of natural log of x. We can't do the input because that would be u substitution, a chain rule thing, so kind of there's only one piece, cosine of natural log. And that makes dv equal to dx. So v is equal to x, and du is, well, the derivative of cosine of something is negative sine of that same something. That something is natural log of x, which has a rate of change of 1 over x. So what are we going to write now? X cosine natural log of x out front, minus the integral of negative sine of natural log of x over x. But, you know, we're subtracting the negative, so I just made that a positive right here. And then when you look at sine of natural log of x, you think, well, that's pretty much that same form we had at the beginning. So I guess we do u substitution again. And in this case, u again is going to be the only real big chunk, sine of natural log of x. And then dv is dx. So v is equal to x, and du is derivative of sine is cosine, still of natural log, chain rule 1 over x. And then we get to the weird part. So let's see what we have. We still have an x cosine of natural log of x. And then, out of here pops out an x sine of natural log of x. Right? We make that multiplication right here. Minus the integral of x times cosine natural log of x. So we actually, those x's divide out. But the problem is, that's exactly what we started with. Right? We're subtracting the integral of cosine natural log of x dx that we started with. And that might seem impossible. It actually would be impossible if we were adding that integral. But because we're subtracting, we can actually add that integral, to both sides of an equation. So even though there's not an equal sign, we actually need to make these two things equal, because then we can add that integral to both sides. And once we add that integral to both sides, well, we get 2 times that integral of cosine natural log of x dx. And all of a sudden, there'd be nothing over here. I guess, weirdly, our integration is done, so we put on a plus c. Now, we're not quite done. We actually didn't want 2 times the integral of cosine of natural log of x dx. We wanted one of them. So we need to divide out that 2. And so we get that the integral of cosine of natural log of x dx is x cosine natural log of x over 2 plus x sine of natural log of x over 2 plus our constant over 2. One little word of warning, c is some number we don't know, but we can't write this as a c here. It has to be a c over 2. Because if we're doing anything, if we have an initial condition, these two c's have to have the same value always. So once we create the c, we have to keep its value, and we divided everything by 2, so that c gets divided by 2 and keeps the divided by 2. How are we going to find the antiderivative of inverse tangent? Well, it's definitely not a derivative we know. We can't use u substitution. I guess it has to be integration by parts. So u is inverse tangent and dv is equal to dx. If du is inverse tangent, if u is inverse tangent, du is 1 over 1 plus x squared dx. And if dv is dx, then v is equal to x. So we're going to say x inverse tangent of x, right? Multiply straight across the top, minus the integral of x times 1 over 1 plus x squared dx. And then you have to stare at that integral and realize that this x up here, that's actually the derivative of the denominator, or at least it's involved there. That x could be thought of as the remnants of a chain rule. Maybe if I put a 2x here, you'll see it. The derivative of 1 plus x squared is 2x. So I put on a 1/2 into 2. And now I can do u substitution in my head. Right, this 1/2 stays out front. The antiderivative of 1 over stuff is natural log of the absolute value of stuff. And you can check that the derivative of natural log is 1 over 1 plus x squared, and then you'd get a chain rule times 2x. Okay, when you look at this, hopefully you're getting close enough to proficient to see we actually have to do integration by parts twice. So we need to choose u is equal to x squared. And the reason I say twice, this LIATE acronym over here on the right, when you take the derivative of a logarithm, natural log, we get 1 over x. It goes away. There's no more logarithm. On the last one, you saw when we take the derivative of inverse tangent, we get nothing like inverse tangent. We get something algebraic. When you take the derivative of an algebraic thing like x squared, in this case, we get a 2x. And that's fine, and it's less complex, but we're still going to have a product rule to deal with. So we're going to write x squared e to the x minus the integral of 2x e to the x. And what I'm saying there is up here we have an x squared. Now we have a 2x in front of that e to the x. If we do this whole process again, which we're about to, we'll have a 2e to the x dx inside an integral, and that we can find the antiderivative of. Okay, so we do u substitution again. In this case, u is 2x. dv is everything else, e to the x dx, which makes du 2dx and v e to the x. Don't forget to copy down x squared e to the x, and then across the top, 2x times e to the x minus the integral, except we're subtracting here, so pay attention to details, I guess. We're supposed to be subtracting an integral, but we're subtracting up here, so that's a minus, and minus a negative integral means we'd add the integral. Anyways, 2x e to the x, and you can see by repeated integration by parts, you know, that x squared, I don't want to say turned into a 2x, but we ended up with another form where there was a 2x where the x squared used to be, and then again a 2 where the x squared and 2x used to be, so we get something much easier. By the time we're done, x squared e to the x minus 2x e to the x plus 2e to the x plus a constant. You can take the derivative of that if you want to check, but you can see if we did do the derivative, you know, we do a product rule, x squared e to the x plus e to the x times 2x, right? That's the derivative of x squared e to the x, and then we do minus, well, the derivative of 2x e to the x is 2x times the derivative of e to the x plus e to the x times the derivative of 2x2. And you can see, if we continued this, that everything's going to subtract to be 0. I'm going to erase that because I didn't have derivative notation. Okay. If you see an x to the 4th e to the x, well, you should know, well, I guess that you should know it's integration by parts. And furthermore, you're going to have to do integration by parts a bunch. You know, when this was an x squared, that x squared became a 2x kind of, became a 2. So in this case, you have to think through, well, it's going to be x to the 4th, and then in the next line, once we do integration by parts once, 4x cubed, and then 12x squared, and then 24x, and then 24. So we can actually do something called tabular integration. I don't know, I might as well show it to you. It's a quick way of doing integration by parts where you do a lot less writing. So we're going to do a whole bunch of derivatives like we would. If you think about it, what did we do to x squared? We took its derivative and got 2x. What did we do to 2x? We took its derivative and got 2. So we're just going to list all those derivatives I said. We'll start with x to the 4th, which has a derivative of 4x cubed, which has a derivative of 12x squared. 24x and 24 completes that line. And then what do we do with the other half? Well, it's kind of hard to see, but this e to the x that we started with, right, that was this e to the x, and we took its antiderivative. And then that e to the x was here, and we took its antiderivative. So we're going to take a whole bunch of antiderivatives, which is pretty easy. And then, we need a whole bunch of additions and subtractions. And the reason for that is, we kind of went through it back here. Let me get rid of this. I talked through it, but hopefully it made sense. You know, on a previous line right here, we could have written x squared e to the x minus 2x e to the x minus the integral of 2e to the x dx. And so the first time we get an integral, you know, as long as there's not a change in sign or something due to the derivative of cosine, maybe, it's going to be minus the first integral, and then that second integral is supposed to have a minus in front of it, but we already have this other minus, so turns out it's a plus. And then later on the next one would be a minus, because it would be like minus the subtraction of a negative integral. So there would be 3 of them. Hopefully you get that. If not, don't worry. You don't have to know all of this. Anyway, so now we just write all of the pieces. X to the 4th e to the x minus 4x cubed e to the x plus 12x squared e to the x minus 24x e to the x, and then along this last diagonal plus 24 e to the x and plus a constant there at the end, which is just shorthand for doing integration by parts. All right, last one, and again, one of my favorites, and the reason it's my favorite is we have a trigonometric and an exponential function, And it doesn't seem like this should work, but you've already actually seen the trick if you watched the rest of this video. So we're going to choose u to be e to the x, even though the exponential's down there on the end, that e, but whatever. So everything else, dv is sine of x dx, which makes v negative cosine of x and du e to the x dx. So we're going to say negative cosine of x e to the x, or negative e to the x cosine of x, and then minus that integral, so I guess it's plus the integral, because that's a negative cosine, e to the x cosine of x dx. And you can see again, same basic structure, so we'll do integration by parts again. And the key here is to keep your u the same. So I chose u to be e to the x, I'll do it again, e to the x. That's animations backwards, let's just pretend that's right. U is e to the x, which makes dv cosine of x dx. And du is e to the x dx, and v is sine of x. So then we get a similar situation that we had before. You know, at the beginning you're like, okay, cool, negative e to the x cosine of x, plus e to the x sine of x, right? We're doing that right here, those two being multiplied, minus the integral of sine of x e to the x, and then you look back up at the top and you realize, oh no, that's what I started with. But if you add that integral to both sides once you make an equation, you can have 2 of the integral of e to the x sine of x dx equals all that stuff we just said. But now we have a plus c at the end because our integration tends to be done. And we can just divide by 2 to get the integral we started with all by itself. And that really does feel like magic. I hope that helps.